perhaps a good place to start is to kind of break down what do you mean by photonic integrated circuits and thin film lithium niobate. So
Sure.
you are the expert.
Yeah,
in this,
yeah.
So,
yeah, thanks for having us today for this conversation. And so the main topic is this thin film lithium niobate photonics. So we'll take a step back. So we just heard a lot about silicon photonics. So these are photonic integrated circuits, which means you can actually guide and manipulate light on the surface of a chip. And traditionally, this light is used in silicon photonics, it's used for communication systems. So you're building transceivers, but I think you've just heard a talk where there's also other innovation where you can do computation on the surface of a chip with integrated photonics. So that's one of the main goals of our platform, and that's because thin film lithium niobate has many unique properties that aren't found in silicon, actually. So this is kind of like we take inspiration from silicon photonics in terms of its scalability, but we're introducing kind of brand new functionality that is very useful. One of which is the electro-optic effect. So this effect has been used of great importance for communication because this is how you make data modulators. And so that's traditionally what lithium niobate has been used for in the market, is actually for data modulation for fiber optic networks. Another really important property is nonlinearity.
Yeah.
So this is a really special aspect of thin film lithium niobate.
right. So nonlinearity, that's another big word. I don't know how many people really intuitively understand what it means. Okay, can you dig into that?
Sure, yeah. So, first of all, every material is nonlinear, but that doesn't mean it's nonlinear in a useful way. Lithium niobate has something called a second order nonlinearity. And this is really important because this allows you, let's talk about what nonlinearity is. So, typically when you use light, you use light just to go from point A to point B. So if I have a laser pointer, it just goes from point A to point B. Nothing profound happens in between. But what a nonlinearity does is it actually can manipulate the light and have it change colors as it travels from point A to point B. And this has a lot of implications, like the quantum effects of light, but also just the fact that you can now change colors and generate new wavelengths.
So in other words, with the silicon photonics, that one side of the light coming into the silicon photonics, basically the same color of light is coming out on the other side.
Yeah.
But with TFLN, we use a TFLN, thin film lithium niobate. One side of the light, one color, and then the other color is coming out, basically.
Yeah, I mean, that's one manifestation of this. And I should say, linearity is important also. It's not just that we care about nonlinearity, because for signal routing, for example, let's look at electronics. So, when you're routing signals from point A to point B, you want that to be linear because you want the data to be transmitted with high fidelity. But, a transistor is a nonlinear element. And so far, there hasn't really been the equivalent of a transistor with light. There hasn't been something so nonlinear you can switch. And to be honest, we're still working on it, but this platform of thin film lithium niobate, we now have the order of magnitude improvement where we have enough nonlinearity to start having a really serious effort on doing doing computation with these optical machines on chip.
So in a little bit of layman's term on this, so with the silicon photonics, you can create integrated photonic circuits. However, with the silicon photonics, you cannot make transistors on the chip. But with the thin film lithium niobate, there's a possibility that you can create the transistors, active device, on the chip. So that's a huge leap from silicon photonics to the next level.
Yeah, I think it is. I mean, the superpower of silicon photonics is how manufacturable it is, and also the fact that, interesting materials can be integrated with it at the same time. But lithium niobate, its secret is all of that functionality is actually baked into the material from the get-go.
Yeah.
And so it's kind of one problem to solve, just manufacturing lithium niobate. There's not a multitude of other problems like how to, combine multiple materials to achieve this functionality. It already has that from the get-go. But until recently, it's just been very hard to manufacture kind of on the same fidelity as silicon photonics. So that's kind of the breakthrough that's happened recently, where we're now actually able to make these photonic integrated circuits.
Okay, so we talked a lot about the material. So what use can this new material can be applied for?
Yeah, I mean, this is really interesting. So in the physics and informatics lab, that we work in with Yoshi Yamamoto, we're very focused on optical computing and coherent network computing with the Ising machine and related architectures. So, that's the first thing that really kind of really kind of got our creative juices flowing, was seeing that, wait a second, the numbers, the performance numbers of this platform are high enough that we can maybe do some really serious optical computing. But like Al was saying earlier, Al Amandi in the earlier session, there's a lot of spin-off technologies and other things that can happen along the way. So I think it's really exciting that actually there's a lot of applications that are starting to pop up.
Mm-hmm. All right. So can you tell us some applications?
Yeah, I mean, one really immediate one is, I guess there's three main things that we should discuss. One is communications. This is perhaps the most straightforward because it's a really well-defined problem with a really well-defined solution. But there's also applications of this platform to new sensing, which we'll also talk about. Lithium niobate can also be a really powerful light engine where you can generate many wavelengths with really unique properties used for sensing. And then there's computing, which is the bread and butter of what we focus on in PhyLab.
Right, right. Can you dig down each one of them a little bit?
I mean, so I guess the motivation for the communications, there's a lot more as of recent. I mean, I think if everyone's been paying attention, these large language models are becoming very interesting in terms of their performance, but they're also getting very, very big. And what this chart is showing is that the growth of the training resources needed for these large language models, it's far outpacing Moore's law. Mm-hmm. And what that means is the only solution right now is to simply increase the number of just make it bigger, bigger, bigger. And that includes optics. So that means we need more optics that are higher performance, that are more efficient. And this isn't really sustainable growth for the LLMs. Like eventually, they have to get more efficient. But right now, there's such a strong business case to just grow as big as possible that's kind of what's going to be happening in the next 5 years. And lithium niobate is poised to play a role in helping some of the interconnects in a data center. And so this is kind of on that topic.
Yeah, so basically with the lithium niobate, that you can kind of create the larger bandwidth communication lines. And as you pointed out, with the LLM becoming larger and larger, you need more basically communication requirements between the servers, between the board, so we can address those areas much more efficiently using this technology, right?
Yeah, no, that's definitely true. I mean, so the number of connections in data centers is getting very, very large. So, I mean, these AI data centers, they're actually organized, and the architecture is different than other more traditional data center architectures. And so you'll need more hardware, faster hardware, and also less expensive hardware, by the way. So I think a lot of photonic technologies will have a very large role in this. Lithium niobate is going to be one of the most exciting emerging ones.
And the chart you are showing here is, I think, made by some marketing research firm, and they're talking about already that lithium niobate, thin film lithium niobate, starts showing up in the market in 2025, and that's growing very rapidly, as you can see. That's by the way, the blue line, not the line, blue areas in the chart. But as you can see, it's a very fast-paced growth is kind of predicted starting from 25 to 28. Can you kind of shed the light? Why is that the case?
Yeah, I mean, this chart tells a few different stories. It really shows you kind of what's going on in terms of communications right now, where for one, we see the purple bars, those are legacy lithium niobate products. These are kind of the generation of products that actually were around for the first telecommunications boom when the fiber networks were being rolled out. But that technology is legacy, and it's really being replaced by thin film lithium niobate, kind of right around now, actually, right around in 2024. And then I think what's so exciting about thin film lithium niobate is that we're going from 0 to 60 right now. Like we're right in the beginning where it's kind of the most exciting time to be developing technologies, investing in technologies, and working with these technologies. But there's many other pieces of the pie. There's 3-5 materials that are really important, and they'll continue to be important. And silicon photonics will continue to have a really large say in this as well.
Okay, great. So shall we move on to the next applications?
Yeah. So we also wanted to talk about sensing today. And what's special about lithium niobate is its versatility. You can have one platform that can do all of this. And normally to achieve this with integrated photonics, you'd have to have kind of a mismatch of many materials going into make some of these devices you can make in lithium niobate with just one material.
Can you, so we are all looking at this kind of rainbow-looking picture here. Can you tell us what it is?
Yeah. So this is work done by Mark Jankowski in Professor Fayer's lab at Stanford, and this is a really special device. So you can shine a single wavelength or close to a single wavelength into this device, and what comes out on the output is a whole rainbow of colors from the UV, which is very short wavelength, all the way to invisible wavelengths in the mid-infrared region. So in a single device, you can basically form a spectrum of color that comes out that you would otherwise need maybe 10 different lasers to accomplish.
Yeah. So in this case, that some of the people know in the telecom that the laser we use in the telecom is typically the infrared areas of the wavelengths. So you cannot, it's not visible for the human eyes.
Right.
But with this lithium niobate property, you just get this light into, and basically all kinds of lights coming out, all kinds of wavelengths coming out. That includes a visible wavelength.
Yeah.
That's kind of like giving, this chart is giving you that how this is done. Am I correct?
Yeah, that's exactly what's happening. And what's special about this is because this chip is smaller than your fingernail, in this very small package, you can now address new applications because this can be used for molecular sensing, for example, where there are signatures of gases, or maybe you could make maybe you could make like the world's most powerful breathalyzer, where you're not just looking for alcohol, you can also do disease detection just by breathing, just by basically shining this light on a person's breath. You could potentially do things like disease detection.
So in a way, you can, with this material, you can create the light source with some pretty wide spectrum, and therefore just shine it through the gas, and then just measure what kind of wavelength was absorbed, and then by analyzing that, you can detect what kind of gas is there. That's it, right?
And we were talking earlier about how photonics is actually really good at sensing. This is the technology used for self-driving cars. One of the big ones is LiDAR, where you basically shine lasers at the environment and collect reflections and signatures that come back. And this is in a sense very similar, only it's at the molecular level, where you can actually be looking at chemical reactions and processes in really fine detail now in a potentially really low cost and portable way. So this is a nice thing that we've realized could be very important for the world in the near term.
And if you want to do something like this without using this property of TFLN, basically you have to have multiple laser sources to mimic the same thing, right?
Yeah.
In a way, the advantage here is that there's just one single source, and you can cover everything. Well, you can cover a wide range.
You can cover a lot. Yeah, that's one big advantage is you don't need to integrate other materials on your platform. You don't need kind of a bank of lasers. Instead, you shine one laser into this device, and out comes a whole rainbow of lasers.
And by the way, this property of kind of one single wavelength going in and it's propagate, that's part of the trick that you are trying to communicate, create that very high level, high speed data center communications as well.
Yeah, that's right. It's what we goes back to why the nonlinearity was so important for us.
And just stick on this one.
Oh, sorry.
One more.
Yeah.
So just a wide range of spectrum. That means, in a way, in a layman's term, that's the kind of white light, right? That, just a regular light bulb includes a lot of wide range of spectrum. What's the difference between just a light bulb, regular light bulb versus this?
Yeah, so I mean, a regular light bulb, well, I guess it's different now that we have LED light bulbs, but a regular light bulb is normally like a thermal source. So they're useful for lighting in a room, but they have very restricted spectrum. It's the black body radiation from that source. This spectrum here, we can completely tailor. We can make it much broader than a black body source, and we can tailor, what wavelengths are emphasized, which ones are de-emphasized. We have very, very good control of the light that comes out, but also the light that comes out is much less noisy than what would come out of a light bulb because there's a lot of coherence of this source. So it really is, more like laser light and less like kind of incandescent light.
Okay.
Yeah.
So not just a white light. It's it has a lot of good
and it's
properties behind it too.
That's right. Yeah, and it's much broader than a light bulb. The wavelengths it addresses is much wider. Yeah.
So great that we may be able to create the new type of sensors, gas sensors as a starting point. But really portable, low-cost sensors could be on the way. It's really exciting. Yeah. All right. So shall we move on to that the last application that you want to talk about? Yeah,
and this gets to the heart of who we are in the Phi Lab at NTT Research, where we're very focused on next generation and new forms of optical computing, like the Coherent Ising Machine. And the important thing to note is optics actually hasn't been very good at computation for a long time.
Mm-hmm. Optical computer has been on discussion for many, many years that I remember, maybe 30, 40 years even. Yeah. So why it didn't happen for the last 30 years, 40 years? I think this chart is trying to explain that, the reasons, I guess, but can you elaborate that?
Yeah, I mean, the big problem is to do useful computation, you need nonlinearity. And a transistor does this very easily. You have current that goes through a channel, and by applying a gate voltage, you can dramatically change the flow of current, which produces a switch. That's a very nonlinear device. But in optics, you've never had that actually. There's no such, you can't easily use one photon to control another photon. They're quite independent entities normally. But in these nonlinear systems, you can actually have the presence of one photon interact with and control another photon. And because of these interactions, you can actually have a richness of dynamics that can be used for computation. So that's the most important thing.
So something similar to transistors in electronics can be created with the TFLN, as you pointed out earlier. And then that's kind of like a building blocks of the computers, so to speak. Yeah.
Yeah.
Are there any other things that you? Yeah.
There's a good analogy to draw. I mean, that's a good analogy. I think our transistors look a lot different. Our transistors, they look like ring resonators where light is circulating on the chip, getting converted to other wavelengths of light and back, and also having the quantum correlations of the light interact with other resonators operating in these, we call it OPO networks, in these parametric oscillator networks. So it looks a lot different, but in the end, there are these basic things. You need nonlinearity, you need memory, and you need gain to do computation. And so that's been the challenge, and we think that this platform is a really kind of big step towards that.
Yeah, with this platform, if we make advancement from here, we may, there's definitely a possibility that we can get those important elements towards the computers. That's what you're saying.
Yeah, and we've worked on the building blocks. So like where we are right now is we have a lot of the building blocks in our back pocket, a lot of the good design work and experimental demonstrations, and we're really working on creating kind of a large-scale integrated system. So we're working on the actual manufacturability so that we can make wafers of these optical computers. So that's a project at NTT Research, and I just want to shout out to one of the previous talks in this session. It's also been shown that thin film lithium niobate can be used actually for photonic neural processors. So the versatility of this material is vast. So it makes it, as a researcher, it makes it something really exciting to be a part of, because you're never working on just one thing because it can do so much.
So in other words, I think you are kind of giving us that this notion that the TFLN will open many doors, potentially many doors for the futures by using photonics to that basically, yeah, photonics integrate, again, the photonics integrated circuits, which can be utilized for many different application, communication sensors, and computations. So that's what, in summary, that you are very excited about.
Yeah. I mean, I think basically, I think this platform, it doesn't really change a single application. I think it changes integrated photonics itself. It's like bigger than one particular application. I mean, all of the circuits made on chip to date have had elements of nonlinearity or particular components that are nonlinear, but with this platform, it's pervasive because it's baked into the platform, and it can be well engineered with a technique called periodic polling. So it's just more pervasive than past platforms.
Okay, wonderful, exciting. So you want to say something about that lithium niobate, it comes full cycle in Silicon Valley. I guess you want to say Silicon Valley someday may be called as lithium niobate Valley or something like that.
Yeah. I mean, and in some respects, it already is, because a lot of the major breakthroughs of the platform happened right here. So this is a special part of the country for this particular part of the world for this particular technology, where some of the first crystal growth was done in Palo Alto and at Stanford University with actually the distinguished scientist from from the Phi Lab and NTT Research, Professor Bob Beyer. So we have kind of a very rich legacy of this material in this area from the 60s and 70s through the 80s, 90s, and 2000. Professor Martin Fayer has carried the torch through the years and continues to play a really active role in the platform. And so it's really exciting to now kind of combine the ethos of silicon photonics, and stand upon all of the achievements that have happened before us.
Yeah, this is kind of like probably some of you on the audience may have seen the history of Silicon Valley, that first transistor was created, and then the Fairchild was created, and then from there, basically the basis of the Silicon Valley, and then just to grow from there. So kind of similar thing is start happening here. Obviously already happened back in 70s, but we are very excited about this new material, which may again one day, people may call this area Lithium Niobate Valley instead of Silicon Valley. So hope that's going to be the case. But do you want to say other few words before closing?
Yeah, no, I mean, it's just a really exciting, as a researcher, it's a really exciting time to work on this technology because, there's the most recent breakthroughs in the manufacturability and the nanofabrication. It's really breathed new life into the platform from, if you're out there and you want to get a PhD, this is a really good topic to do it in, integrated nonlinear optics, but we're also at the point where it can be commercialized. And so it's not just a peculiarity that happens in an academic lab. It actually is going to be entering the marketplace and play a really important role here on out. So it's exciting.
Okay, great. Thank you very much, Tim. So great talk. And we at NTT Research that we are really interested in this material. And stay tuned. We're going to continue making progress on this one. So thank you very much, Tim.
Thank you.
And thank you very much, everyone.